So what is the difference between a chemical and a physical change? Well, for starters, chemical changes occur when new substances are formed, and those new substances have a new chemical formula that's different from the last. A chemical reaction is required to undo a chemical change because a chemical reaction has occurred. Physical change, a substance has not changed its identity. The substance has the same formula as it used to. There are no chemical bonds broken, and it could be reconstructed to the original without a chemical change. So those are, real quickly, some of the basic ideas. So what are we talking about here? Well, let's look. If we look at, take a substance like ice. Here is solid ice. Ice is composed of water molecules. If we zoom in here, we can actually find a water molecule. This little H2O right here, this little thing right here, is a water molecule, H2O. And if you still have two H's connected to an O, you will still have water. And it's going to take some change in that arrangement to not to have a chemical reaction. Anytime we change anything else about this arrangement, we do not have chemical change. We actually have to physically separate those bonds on those H's to O's to have a chemical reaction. So let's look as an example here. If we look at this, we can see this is the solid with a nice little arrangement, very predictable pattern. We can turn it all sorts of different ways and see patterns of symmetry. And if we go ahead and warm this up, we'll see that as it gets warmer, these water molecules begin to move around a little bit more. They vibrate a little bit more rapidly, and they begin to leave their pattern. And what we're watching right here is actually ice that's melting. The water molecules themselves are not melting because melting has no meaning with respect to molecules. What molecules are doing, whether they're packed tightly or moving around rapidly, determines whether they are solid or liquid. So if we were to pause this now and go back and start looking for those patterns that we saw earlier, we're going to see that they're not to be found. We have a kind of a chaotic mess. We can't get back that nice little orderly arrangement because we've melted it. And so that's what liquid water would look like. However, if we zoom in on that same little water molecule right here, it's still H2O. It's still made of water molecules. There's no change in the chemical identity. So this is still water. It was H2O. It remains H2O. This transition of melting from a solid to a liquid, ice to liquid water, is a physical change. It would fall into the category of physical change. Similarly, if we were to take something and evaporate it, say for example that we have a say that we have some molecules here, some nitrogen and oxygen molecules, and we zoom in on here and we look at these things. We have, this is an N2, this is an O2, these are our Hofbrinkels. That little atom in there is unattached, and so these are diatomics. That's a molecule. That a pair there, that's a pair, that's a molecule. And if we allow this, this is currently liquid air. This is what nitrogen, oxygen and argon would look like if you compress them to a liquid. Now let's allow it to go to a gas. If we allow it to go out to a gas, we will see that nothing happens because this simulation is really lagging behind. And there it begins to... Well, this goes a lot faster when you're not also trying to record video. But you can see that those things are beginning to come apart, spread out, and there we go. So that would represent evaporation. That's when a liquid turns into a gas. What you're seeing there would happen. If we look in, all of the little molecules are the same. Their bonds haven't changed. They're still connected. So that, in a nutshell, is what we mean whenever we talk about a physical change. As long as the molecule hasn't changed, it's a physical change, not a chemical change. And so let's look at some keywords that we can look for to suggest whether something is a chemical change or a physical change. Keeping in mind our keys. Don't change its identity, don't change its formula, then it's physical. If you could reconstruct it without a chemical change, if no chemical bonds are broken, those are all physical. And in chemical changes, if you have a chemical reaction, a new substance being formed, or it requires a chemical reaction to undo the change, then you have a chemical change. So if we just kind of go through here, there are some, it's not obvious from the word itself, but as you familiarize yourself with some of these words and keywords that kind of give away different sorts of ideas, and we might talk more at another time about why some of these are, but we'll just kind of get some general ideas here. If you take shred, if you shred paper, is it still paper? Well, yeah, it's still paper. That's physical change. If I burn paper, is it still paper? Well, no, it's now carbon dioxide and ash, so that would be a chemical change. If you combust, well, that's a synonym for burn, so that would go there. Boil. Boil is what we just saw. We saw how nitrogen oxygen boiled without changing the chemical bonds. In fact, any kind of transition of phase, boiling, freezing, melting, condensing, any of those things would go into the physical category. So be aware of that. Ooh, didn't mean to grab that. And sublime is a word you may not know yet, but sublime is the transition from solid into gas. That's another physical state transition, so it would go over in this column. Think of dry ice. Dry ice sublimes. Tear. If something tears, that would be physical again. Corrode. Ooh, corrode's in there twice. We only need it once. Corrode. Corrode, if a battery corrodes. Corrosion is generally the result of some kind of a chemical reaction, and so that would go there. Decompose is another chemical term, usually not because it has to be per se, but it usually is kind of a dead giveaway that you have a chemical reaction. Tarnish kind of goes with corrode. If silver tarnishes, if something rusts, that would be a chemical reaction. Healing. Healing, if let's say you cut yourself and your wound heals, how does that happen? Well, your body makes new skin cells out of things you eat, and that requires chemical reactions. Digestion also requires chemical reactions, things in your body turning nutrients and stuff into new cells. And dissolving, actually, for fun, can go in both. You got to be careful with dissolving. If you take acid and dissolve it, a metal with it, that would be chemical. And but if you take, generally when you dissolve things in water, those things are physical changes. And if you think about it, I can explain why the difference occurs. If I take metal and dissolve it in acid, let's go back to this idea that if you can reconstruct it without a chemical reaction, then it's a physical change. So let's go back and talk about our examples. If I take magnesium and dissolve it in acid, I will now sit and let the acid dissolve evaporate over time. If I just let it sit out on the counter over time, what I will have is a white crystalline powder. My magnesium didn't come back. So that would be evidence that that's a chemical reaction. However, if I take salt and dissolve it in water and let it sit on the counter over time, and you can try this at home if you don't believe me, you will get the salt back. And so ionic compounds that are dissolved in water, that is a physical change, whereas when you generally dissolve things with acids, the test is just to let it sit out on the counter for a few days and see if it comes back. But in general, when we dissolve things into water, we can expect those to be physical changes. Whereas if we dissolve them into acids, it's going to be chemical.